Okay, we carry on question 14. I hope you have tried. Okay, where is it possible for E field to be zero at a point where electric potential is not zero? So let's try and write down this question. Right, can E field equal zero if V not equal zero? Right, and there are a couple of cases where we find this is true. In fact, these two can be considered one case, but let's look at them individually. Right, so let's have a look at a point X here, equal distance away from two positive charges. Right, will the potential here at X be zero? Right, clearly the answer is no, because the potential at X will be given by 1 over 4 pi epsilon naught plus Q over D plus 1 over 4 pi epsilon naught plus Q over D. So actually it's equal to 2Q over 4 pi epsilon naught D, right? But so the potential is not zero, right? But can the electric field strength here be zero, right? Then the answer should be yes, right? Because if I look at the field strength at X, right, the field strength due to this charge is in this direction, right? And this field strength is equal to 1 over 4 pi epsilon naught Q over D squared. And the other one is this direction from this charge, right? So E equals to 1 over 4 pi epsilon naught Q over D squared. Since they are equal magnitude and opposite direction, right, therefore the E field here is 0, right? So in this case, it's very clear that at X, Vx is non-zero and electric field is 0, right? So potential is non-zero, electric field is 0, right? And actually this case, right, if you graph it, it can look something like that, right? So this is where your plus Q is. This is your plus Q, this is the other plus Q. So if you draw the potential against time x graph, right? Roughly speaking, it should look like that, right? And if you look at these three parts, this part, and this part, right? This part almost is actually an asymptote, so I won't say that it actually hits v equals 0, but if we assume v equals 0 here, right, then the E field is 0 as well, because the gradient here looks like it's the tangent to the curve at this point looks like 0 gradient, right? So where else can I get E field is 0, right? This point, right? You can see the tangent drawn at this point is such that the gradient is 0, right? Remember E is minus dV dr, right? So E field here is 0, but is V 0 here? Clearly not. In this case, V is not 0, right? So these are two cases at X here, right? And at X here, right? There are cases whereby E can be 0 even though V is not 0. Right, move on to electric field strength of a uniform field between charged parallel plates. Okay, so these are 3 LOs we'll try and go through. Right, so remember parallel plates from earlier, right? This is actually the more common diagram that you draw, okay? Always goes from positive to negative, equal distance within the plates, okay? And obviously the direction of the field lines is from positive to negative, right? We can use a formula here in given by this formula. Electric field is change in potential, which is potential difference, modulus over D. Right, this formula is actually derived from this one, the earlier formula over here. Right, so we don't care about the sign, we just care about the strength of the electric field because we know the electric field direction can be told from other ways. Right, so electric field is modulus of delta V over D. So we can try this question over here. I think a diagram is given. Right, you can pause and try. Two large plates separated by 4 mm, lower plates -6, top plate. What should the top plate's potential be to create an electric field of 400 volt per meter upwards in space between the plates? Right, so I hope you have paused and tried the question. If not, please do so. Okay, now we are going to go through the answer. Right, so what is the potential at the top? Right, we have to unpack this formula over down here. So the electric field we know is clearly Okay, so we're using formula E equal to delta V mod over D. Right, electric field is 4,000. Right, delta V, we take the higher minus the lower lah. But in this case, minus 6 at top, who is the higher one? Right, since it's the mod, right? So we just take the higher value and minus the lower value. Right, we should realize that actually minus 6 is the higher value because electric field direction is always from high potential to low potential. So if it points this way, this is the high potential and this is the low potential, right? So the high number minus 6 minus the low potential, which is V top, right? Then this is how we find V top. Then divided by D, which is 4 mm. Right, so 4 mm, if we want to put SI unit, is 4 times 10 to the power minus 3 meter lah. Right, so how to find V top, right? So we'll just 4,000 multiplied by this, so 10 to the power minus 3, so it's 16 lah. So it's 16 plus 6 equal minus V top. So V top is equal to minus 22 volt, right? Okay, oops, I made a mistake. Did I make a mistake? Oh no, yeah, V top is minus 22 volts. Yes, it's correct. Right, again. Moving on. Right, so we look at forces on charges in uniform electric fields. Right, so if we have a charge inside here and here, actually the formula is very simple lah. If I want the force on this charge, I just take F equal QE. Right, I take the charge multiplied by the field strength because field strength is constant嘛, right? And since E is given by delta V modulus over D, I can substitute E to be this one. Right, so this is the formula I get here. Right, so you can try this question and oil drop. Right, so in this type of questions, right, you need to pay attention to the difference between oil drop and electrons. Generally, in this type of question, right, oil drops we consider to have its own weight, but for electrons, we only care about the electric force. We don't care about gravitational force because gravitational force is too low. Right, later on we'll have a question that addresses this discrepancy between for an electron, right? How much bigger the electric force is over the gravitational force. Okay, but anyway, just pause and try 17. Okay, we're back from the pause. All right, this is a minus Q charge situated between two charged parallel horizontal plates as shown in the diagram. The separation of the plates is D. Droplet is observed to be stationary, means in equilibrium. Right, upper plate is plus, bottom plate is negative V. For this to occur, the weight of the droplet must be equal in magnitude to which one? Right, so this type of thing, draw free body diagram. The weight is like that. Then the outward force must be F electrical. Right, F electrical, as we learned earlier, is always charge times electric field in a parallel plate, which is a constant. And we already know electric field as above is V minus V, right? Because actually, you think about it, this is some positive number, let's say positive 20, and this is some negative number, negative 20. So what's the difference between this? Hopefully you can see it's 40. Okay, can? Right, so that's the idea behind this, right? And divided by the distance between them, which is D lah. No, it's D, so we just leave it alone. Right, so that will give you 2QV over D. Right, 2VQ over D, so should be B. Right, solution is B. Okay, right. Quickly try example 18. All right, very similar type of example. Okay, we're back from the pause. Okay, again, is this an oil drop? Yeah, I think you have to assume it's an oil drop, right? They didn't really describe what Y is. Oh, it's a sphere. A sphere definitely have weight, right? So again, free body diagram, this is weight. If it's suspended stationary means equilibrium again. So therefore the electrical force is up, right? So we have to look at options and guess whether which one can give me an electrical force outwards. Right, so let's try. A is negative, plate X is which one? Plate X is negative, okay, so plate X is negative, sphere is positive, plate Z is negative. Right, this one a bit unclear because depends on this negative and this negative, which one is more negative. Right, so you point from the less negative value to the more negative value. That's the electric field direction, right? And yeah, so this one unsure. Let's question mark A first. Plate X negative, This one is positive again. Plate Z. Okay, this is a little bit better because if positive, negative, right, then I know the field is like that. Then if the field is like that and this positive charge, you can see the force is definitely in this way. So F electrical. So this one is definitely possible already. But we check the rest lah. I think B is the answer, but let's check the rest. Plate X is positive. Plate Z is negative. So the field is this way now. And charge is positive. If charge is positive, then the force on the charge must be in the direction of the field, which means F electrical is down, which means wrong already. Right? F electrical has to be up for equilibrium. Right? Plate X is positive. This one again question mark. Right, so the answer has to be B. Right? A and D is cannot really tell the correct answer. Right? B is definitely correct. C is definitely wrong. Okay? Right. Are we up to this is the explanation. Okay, but we talked about this already. So not to worry too much. Right, I think we'll come back for the next part in the next session.